my partial differential equation solver PD 2D, whether you're solving 1D, 2D, or 3D problems, whether it's time-dependent, steady state, or eigenvalue problem, linear or nonlinear, you end up solving a linear system. And in fact, for 2D and 3D problems, the vast majority of the computer time is spent in solving these linear systems. So if you want to solve partial differential equations efficiently, you need to learn how to solve linear systems efficiently. In Chapter 4, we're going to talk about iterative methods for solving linear systems. These are very efficient for certain special linear systems, but PD2D relies mainly on direct solvers, that is, Gaussian elimination-based solvers, because for general, complicated, non-symmetric systems, most iterative methods simply don't converge, so you have to rely on direct solvers. So that's what Chapter 0 is about. Gaussian elimination as programmed on the computer is very similar to what you learn in matrix algebra, with one significant difference. In matrix algebra, you learn to reduce your matrix to upper triangular form. You take multiples of the first row, add it to rows 2 through n to eliminate the elements below the diagonal in the first column, then you go to the second column, and so forth. And in matrix algebra, you learn that if one of your diagonal pivot elements is 0, then you have to switch that row with another row below it to bring up a non-zero. Of course, if they're all 0, then you have a singular system and you have to quit. If you're programming on the computer, that means you have round-off error and you're not doing arithmetic exactly. Then it's important that the pivot not only not be 0, but not be small. So there are various strategies to achieve this. The most popular by far is partial pivoting, whereby one takes looks at all the potential pivots, that is AKK all the way down through ANK, and simply looks for the one that's largest in absolute value, switches rows to bring it up, and then you have the largest potential pivot possible in the diagonal position, and you proceed. And that's usually a pretty good strategy. Then once you've reduced it to upper triangular form, of course, you do back substitution, solving for the last variable and so forth in reverse order, same as in matrix algebra. Now in our text, we have a linear system solver called LINEQ. In Fortran, there's a MATLAB version in the back of the book. This programs the straightforward Gaussian elimination for a full linear system with partial pivoting. Outer loop here, K is the column counter. You start with column 1 and go through column n-1. There's nothing to knock out below the diagonal in the nth column, so you only go to n-1. Then you switch, look for the largest potential pivot, and then you switch rows to bring the largest pivot up. Then you're in column K. You look at all the elements in column K underneath the diagonal, that is in rows K plus 1 through n. For each one of these, you simply add a multiple of the kth row to the ith row. And here is where all the computer time is spent for large systems. Nearly 100% of the computer time is spent in this one loop here, because this is the only triple nested do loop in the program. Notice that the choosing the pivot and actually switching rows is only a double nested do loop, so that's order n square work. This is order n cubed work. In fact, you can see that it'd be less than n cubed. Here we can see the count the amount of operations if you throw away everything except the main 3 loops here. This is the column counter for each column K. You knock out elements K plus 1 through n in that column, and here you're actually taking a multiple of the kth row and adding it to the ith row. If these were all 1 to n, 1 to n, 1 to n, it would be exactly n cubed multiplications. It's clearly less than n cubed. It works out to about 1/3 n cubed operations. for a full linear system solver. Now we just noticed that the pivoting it requires a negligible amount of work for full linear systems, so why would we worry about pivoting? Because we'll see later in solving banded linear systems and general sparse linear systems, it's not a negligible amount of work, so sometimes it's important to know if pivoting is really necessary. And the next section talks about a couple of types of matrices for which pivoting can be proven unnecessary. One is a diagonal dominant matrix. That's a matrix such that in each row the diagonal element is larger in absolute value than the sum of the absolute values of all the others in the row. And it's proven that for such a matrix, pivoting is not necessary. Another type of matrix for which pivoting is not necessary is a positive definite matrix. A positive definite matrix, so one definition is it's a symmetric matrix, therefore all eigenvalues are real, and to be positive definite, all eigenvalues have to be strictly positive. And for positive definite matrices, it's also proven that Gauss elimination with no pivoting can be done without concern about a zero pivot. Now, most linear systems that we'll encounter in solving partial differential equations, nearly all, are sparse. They'll typically be very large but very sparse. That is, most elements will be zero. Now the LINEQ routine that we just saw appears to take advantage of zero elements. If an element is zero, it will skip it and not try to knock it out. However, if you have a random sparse pattern, that is, if your matrix has a small number of non-zeros but they're scattered randomly about the matrix, LINEQ really doesn't do a very efficient job taking advantage of zeros because of fill-in. As you go through, by the time you get halfway through the matrix, the remaining lower right-hand corner of the matrix will be nearly full, so maybe you'll cut computer time by 50% or so, but not dramatically. However, if you can order the unknowns to put the matrix in a band form, and nearly always we can in our applications, then you can take much better advantage of zeros with Gauss elimination. For example, here's a band matrix with 2 subdiagonals and 3 superdiagonals, then a total of 6 diagonals, non-zero diagonals. And if you go through normal Gaussian elimination here and you don't do any pivoting, then the elements outside the band all remain zeros. You take a multiple of this and add it to that, knock that out, multiple first row, add it to the third row to knock that out, then you simply skip all these. Meanwhile, you're only changing these elements here. Let's say we're down to the third column, then you only have 2 elements to knock out below the diagonal. You skip all these, and only the elements inside this box change, so the elements outside the band above and below remain unchanged, and the total amount of work is cut dramatically. Now the outer loop is still 1 to n minus 1, but you only have, let's say there are L subdiagonals and L superdiagonals, then you've only got L elements to knock out, and it takes L operations to knock each one out, so basically n L square multiplications, which will generally be dramatically less than 1/3 n cubed, assuming L is much smaller than n. Now, if you, what about if you have to do pivoting? Then that does make it a little bit more inefficient, but not much. If you do partial pivoting, what happens? Well, the elements below the band remain zero. Some of the elements above the band fill in, See, in the worst case, let's say we're on the third column here. The worst case, you might have to change switch the third and the fifth columns, and that will fill in up here. So you'll basically get, if there are two subdiagonals in the band, then you'll get two extra superdiagonals. If the number of sub and superdiagonals are both L, then you get an extra L superdiagonals and no extra subdiagonals. And it basically doubles the amount of work, because now the outer loop is 1 to n for each column. You still have L elements to knock out, because these still are 0. But now to knock each one out requires 2 L multiplications rather than L. So you basically double the amount of work and increase the amount of memory by 50%. But that's still dramatically better than 1/3 n cubed. So pivoting doesn't hurt that much when L is much smaller than n, as it normally will be for our applications. So now if you do partial pivoting, if you don't do any pivoting, the triple nested loop where all the work is done in your band solver looks like this. Again, the column counter goes from 1 to n minus 1. Now you knock out elements only k plus 1 through k plus L, and it takes L operations for each one. If you do pivoting, the only thing that changes is this inner loop now goes from k to k plus 2L. There is a band solver in the book, actually one for a situation where you don't have to pivot. Then there's L band, which does partial pivoting. Looks pretty much like LINEQ, except there are only L elements below the diagonal to knock out, and it only takes 2 L operations to knock them out. So the total amount of work is approximately 2n L square. Notice also that the matrix is not stored as an n by n matrix. That would be very inefficient. There's no use in even storing the elements below the band or above the part of the band that fills in. So the matrix is actually stored as an n by the second subscript goes from minus L to plus 2L. Let's see how this is stored. Okay, the matrix is an n by, in this case, n by 5 matrix. If there's 2 subdiagonals and 2 superdiagonals and 1 main diagonal, then it would be stored as an n by 5 matrix, and that makes the subscripts slightly more complicated, but not much, and it takes advantage of the zeros outside the band. For the simple case L equals 1, a tridiagonal system where you only have 1 subdiagonal and 1 superdiagonal, if you do partial pivoting, then you may have 1 extra superdiagonal fill in. The D here, the D's start out at 0 and they may fill in, so you only have to store 4 diagonals, 3 supplied by the user and 1 which begins 0 and fills in. And there is a tridiagonal solver in here also, in the equivalent MATLAB program in the appendix, where here the user, instead of supplying a n by 3 matrix, supplies the 3 diagonals in 3 vectors, and D is set to 0 initially, but because of pivoting it may fill in. So you have a slight increase in work due to pivoting, but it's not very important. In Chapter 4, here's shown a typical linear system, a matrix that results from a finite difference method applied to a 3D problem. And as you can see, it produces a band matrix. Here's the bottom diagonal of the band, and here's the top diagonal. And everything above that, since there's pivoting turns out to be not necessary, this matrix turns out to be positive definite. Even if it were necessary, it would only double the amount of work. But for this case, since no pivoting is necessary, all the elements below the band and above the band stay zero. They're never touched, they're never even saved. But notice that the elements inside the band are mostly zero also, and this is typical of 2D and 3D problems. And the band solver, although it takes advantage of the zeros outside the band, does not take advantage of zeros inside the band. These are going to fill in, and so we think that there might be some way to do better than a band solver. Certainly the iterative methods take more full advantage of the zero structures, but we can't rely on iterative methods for difficult linear systems. Is it possible to modify Gaussian elimination to take advantage of the zeros even inside the band? And the answer, somewhat surprisingly, is yes. There are so-called sparse direct solvers which are not band solvers. They take advantage of sparse structure even better than band solvers typically, but the matrix does not have a band structure. Now, these are rather complicated methods. They're beyond the scope of this book for the most part, but can give a little insight into how they work. They're actually quite complicated to program and efficiently, but get some idea of the idea behind these methods by looking at a couple of linear systems here. These are actually essentially the same linear system, but with the rows and columns ordered differently. On the left, the X's represent elements which are non-zero in the original matrix. In the case of this matrix, the entire matrix fills in as you go through the Gaussian eliminations. You take a multiple of this row and add it to that to make that zero, and this whole row fills in. Multiple this and add it to that, the whole row fills in. By the time you've eliminated the elements in the first column, you've got a full matrix, and so it's basically going to take order in cubed work, same as if it had been a full matrix to begin with. On the other hand, here we have the same matrix. We've just moved the first column to last and the first row to the last, and now there's absolutely no fill-in. You take a multiple of the first row and add it to that. This element changes, that element changes, no fill-in at all. Go through, and it basically is order n work, so a dramatic decrease in the amount of work simply by reordering the unknowns and the equations. And basically the principle is behind these sparse direct methods is to try to postpone fill-in as late as possible where it does the least damage. You see, you want to save rows that have a lot of non-zeros in it. You want to order them last so that they don't have time to fill in. These, as I said, these methods are rather complicated to program, but that's the basic idea of these minimal degree algorithms. The ordering is key here. That's the difficult part of these algorithms, is ordering the unknowns in the equations so that at every point in the Gaussian elimination, the row, the next element which is to be eliminated, is the one that has the least number of non-zeros on its row, and therefore causes the least amount of fill-in, and that's a non-trivial task to do. But there's an example in the book to illustrate how you can do better than a band solver. Here's a linear system. It's where a band ordering is used, and as you can see, there's fill-in inside the band, so it's not taking full advantage of sparseness. Now here's exactly the same matrix, but ordered by an approximately minimal degree algorithm. And as you can see, the idea is that the fill-in is postponed as late as possible, and there's actually less fill-in here than with the band solver, and therefore less work and less memory requirements. It should be mentioned that for the sparse direct methods, minimal degree algorithms, it's even more important to avoid pivoting. For the band solver, if you have to pivot, it basically doubles the amount of work. For the sparse linear system solvers, it may increase the amount of work a lot more than that. It can still be done efficiently, but it's much more difficult, so it's nice to have a positive definite or diagonal dominant system if you're going to be using a sparse linear system solver. For that matter, the iterative methods generally work better for diagonal dominant and positive definite matrices also. Now there's one topic we skipped. There's a section on the LU decomposition. This is basically designed to make it possible to solve several linear systems with the same matrix and different right-hand side efficiently. If you're solving one linear system using Gauss elimination, and we'll just take we'll assume it's a full matrix now, but the same applies to the band and sparse systems. You're solving a linear system AX equals B, and as you go through the Gauss elimination, reducing to upper triangular form, basically all you have to do is save the multiples. Let's say M21 is the multiple of row 1 that you used to add to row 2 to eliminate A21, and basically you eliminate this element, and then instead of putting a 0 there, you know it's a 0 and you won't forget it's a 0, but you put the negative of the multiplier that you used to 0 that element, sort of a trophy of battle to remember how you got rid of that element by, and do the same thing here. Put the negative of the multiplier that you used to eliminate that element, and so forth. And when you get down to upper triangular form, you do the back substitution as usual, remembering that these elements below the diagonal are all 0, even though we've got something stored in them that's not 0. We know they're really 0. So you do the back substitution as normal. Now, if you need to solve another linear system, different right-hand side, but same matrix, there's no need to go through the Gauss elimination on the matrix here, because all you need to know is what multiples of B1 to add to B2, and there's your multiple, and what multiple of B1 you need to add to B3, and there's the multiple, and so forth. So you can go through and do all the forward elimination to B only, and you know you're going to end up with this upper triangular system, so now you can do your back substitution, and basically you don't have to touch the matrix A, you just touch the right-hand side B, and here are your multiples. Tells you what multiple of BI you have to add to BJ to do the forward elimination, and then you've got your final upper triangular form, and so you know how to do the back substitution. So it turns out that the first time you solve the linear system, it takes, of course, 1/3 n cubed multiplications, but for absolutely free, it doesn't cost you anything to save the, it's called the LU decomposition, basically saving the multipliers, and in case you need to solve another linear system with the same matrix. And now the amount of work to solve the second and third linear system and so forth is only order n squared, so have a dramatic decrease in work. And if you have a sparse or banded system, the same thing is true. It still cuts the amount of work significantly, because you don't have to do the forward elimination to the matrix that's already done. You just do it to the right hand side.